All right, these are supplemental problems for lesson 2 on Coulomb's law. Okay, so this assignment is going to go over the questions and the problems, and some of them were pretty complicated that were presented in the Coulomb's law lesson. So let's go ahead and get started with that. I'm going to start off by at the very top of this writing the formula for Coulomb's law force, and it's force, and this is electrical force, so you can put a small e equals Coulomb's constant times the charge between the two objects. In this case, they're usually electrons or an electron and a proton, but not always, over the distance squared. All right, and Coulomb's constant, I'll write it down up here. Okay, that is Coulomb's constant. That's the value of K. Sometimes students ask, what do all those units mean? What they do is they make, when you do any problem with this formula, they make the units cancel out so that the proper units of measure are left in the end. So if you put in two charges, that's Coulomb times Coulomb over distance squared, that would be meters squared. It will cancel everything out here except newtons, and you'll end up with newtons of force. What if you were trying to solve for distance? You were given a force, charge in coulombs, then what you would do is when you solve that problem and eventually solved for d, you would end up in units of measure of meters, because that's what distance is measured in. So what this does, it looks kind of scary, but what it does is it tells you, a constant like this tells you what the units of measure you're working in. For example, newtons rather than pounds, or meters rather than centimeters, or yards. It tells you the units you're working in, and it assures that they'll cancel appropriately, so you end up in the final answer with only the unit that you want. Okay, so let's look at the first question. This is from the instruction video of Coulomb's law. If the distance between two charges of a particle is increased by 4, the force will decrease by a factor of what? Okay, by the way, I referenced the square that we're talking about. So square 2, this question's actually in square 3. So those are the squares on the bottom that you see that allow you to progress or take the video back. By the way, you can't progress videos. You have to watch them in order. Once you've watched them all, then you could go back and move back and forth between them. Okay, be aware of that. All right, so let's take this formula and let's just ignore everything except distance squared, because we're interested in the relationship between distance and force here. And the way that's written is force is proportional to 1 over distance squared. Now that's not an equation, a math equation, because it's a relationship. That there's a relationship between force and what's called the inverse, that is the reciprocal, 1 over the distance squared. But let's treat it as though it's an equal sign for a minute. We're just going to say this. We're going to ignore K, Q1, Q, and this should be Q2. We're going to ignore K, Q1, and Q2. So let's just take a couple of examples. Sometimes when you're trying to work out a relationship like this, you just play with some real numbers. So let's go ahead and say distance is 1 meter, okay, or just 1. Then that means force would equal 1 over 1 squared, which would equal 1, whatever our unit of measure is. It could be meters, could be whatever. We're just trying to get a concept here. Now let's say we increase the distance to 4, because that's what it says it wants to know. The distance between two charged particles is increased by 4 times. What will happen? What will happen then is that the force will equal 1 over the new distance. Let's just say now it's 4 meters. That's 1 over 4 squared, which equals 1 over 16. So intuitively, you should say that when you make two charged particles move apart from each other, they're not going to have as much force. That should be kind of intuitive to you. That should make sense. If you're a billion miles away from the Earth, you're not going to feel the Earth's gravitational pull. Whereas when you're right here on the Earth, you do feel it very strongly. So that's what it's saying. If you move them apart, it's going to get weaker. And so the answer to this is 1/16 And I don't like you to write fractions like this, but I don't have any space to write it 1 over. You should write 1 over 16 to be proper. So it says the force will decrease by a factor of 1/16. The way I like to say that is the force will be 1/16 as strong, which is the same as what they said. Will decrease by a factor of 16. It'll only be a 1/16 as much electrical force between those two particles as at 4 meters as there was at 1 meter. Okay, so I give you a couple of practice problems to do down here with that. These are not on the video, but they're just a chance to practice that. Okay, now what happens when you double the distance between the two particles? So again, we'll say force equals 1 over distance squared. We're not interested in the Q1, Q2, and K right now, just the relationship between these two. So again, let's say we start at 1 meter. So that would be 1 over 1 squared equals 1. Now we double it, so we go to 2 meters. That would be 1 over 2 squared, and that equals 1/4. So you can say 1/4 as strong, or it's decreased, their wording, that's decreased by a factor of 1/4. Okay, what about if you cut the distance in half? Now you're bringing them closer together. So when you pick a number, you want to pick a number that you can divide by 2 and not end up with a decimal or some weird fraction. Okay, so we're going to again say that force is 1 over distance squared. So let's just start this time with a distance equal to 4. So 1 over 4 squared, and that would be 1/16. Now again, we're not interested in this number specifically. We're interested in the relationship when we cut the distance in half. So that would be, let's say we cut the distance to 2. That would be cutting the distance in half to 2 meters. So that's going to be 1 over 2 squared, which equals 1/4. So what's the relationship between this? Well, if you can't just look at it and see it, you could put this number over this number, but what the answer is, it would be 4 times stronger. So cutting the distance in half doesn't just make it twice as strong, it makes it 4 times stronger. Okay, so again, if I wanted to make a ratio of that, 1/4 over 1/16. Okay, do this on your calculator if you need to. That equals 4, so it's 4 times stronger. What if you triple the distance between them? So force equals 1 over distance squared. Again, it's really proportional, but we're ignoring K, Q, and Q. So let's say distance is 1 meter. Now we're going to triple it to 3 meters. So this would be 1 over 1 squared, which equals 1. And this one would be 1 over 3 squared, which equals 1 over 9. So you could say it would be 1/9 as strong. It gets weaker as you move them farther, apart. Okay, you cut the distance to 1/3. So we're going to find a number we can easily cut to 1/3 of its value. So let's go ahead and say distance equals 9 to begin with, and after the distance equals 3. So that's cutting the distance from 9 to 3 is cutting it to 1/3. So that's 1 over 9 squared. Yeah, let's make an easier number here. Let's make this one 3. You're going to get into some big numbers there. Again, my point here is you can make up numbers that do what it's asking you to do, that indicate that. So let's say the distance starts off as 3, and we bring it to 1/3 as far, so that's to 1 meter. That makes the numbers a little smaller. So this is 1 over 3 squared equals 9, and this is 1 over 1 squared equals 1. So that means the distance, or excuse me, the force would be 1/9 as strong. That is 1/9 of that. So 1/9, it would become, I made a mistake there. Okay, so we're gonna cut. Okay, so we're gonna cut the distance to 1/3. So we start at 3 meters, we cut it down to 1 meter. So that's gonna be 1/3 squared. That equals 1/9. And this one would be 1/1 squared. That equals 1. So going from 1/9 to 1 is 9 times stronger. 1 is 9 times greater than 1/9. So it is, that's that, it is 9 times stronger. Again, as you bring something closer, it becomes stronger. So this is called the inverse square law. This relationship, force is proportional to 1 over the distance squared. All right, we're going to move on now. And we are going to do a problem that's on square number 4. All right, so we're going to move on now, and we're going to do a problem that's on square number 4. And it's basically an application of Coulomb's law between two charges. And it's oftentimes helpful to draw pictures. So it says a positive charge of 5 microcoulombs and I'll deal with that little symbol in just a second. On the x-axis, a negative charge Q2 of 7 microcoulombs, so this is negative, is 0.8 meters away. So we're on the x-axis. It doesn't matter what axis you're on, but it just means there can only be a straight line between those 2 points, and that's 0.8 meters away. Find the force and direction applied by Q1 on Q2. First, you want to kind of look at the situation and say what's happening. Well, they're opposite charges, so they're going to be attracting each other. Whenever two charges move towards each other, you're going to end up with a negative force. It's the way the equation is set up. If two things are pushing away from each other, it's going to be a positive force. The negative force just simply indicates direction. And just think about it. When you push on something, you think of yourself as putting a positive force on it. When it's coming towards you, we just have to define that as the opposite direction, so that's going to be a negative force. Okay, now, I've put together a sheet here and show you a formula sheet for this particular lesson and really future lessons as well. And this is also includes all the formulas in the electrostatics lesson, which is lesson 1. And here's all the formulas. So F equals QE, and it includes the units of measure along with them. And down here at the bottom, you'll see a table of these prefixes. So the one that they're using this time is this one right here. It's the Greek letter mu. It's not important you know it by name, but it's micro. And that means 10 to the minus 6. It's 1/1,000,000th of a whatever you're talking about. Coulomb, meter, whatever. Micro. So wherever you see that, you can write the scientific notation as whatever the number is times 10 to the minus 6th. Okay, and this again is in the Google Classroom for you. You can print this out if you would like. That's probably a good idea if you can. I'm going to keep adding to that sheet. I haven't ever had a chance to go through every lesson and put together every formula, but I'll build that as we go along. So here's Coulomb's law. And we said that this one, they didn't identify which charge is which. Yeah, they do. Q2. Okay, so this is Q1, and this is Q2. It does not matter, but we're going to just call it that. So I recommend that you always write out the formula first. When it's easy to identify, this one's easy. It's the only formula in the unit. Is K times the charge on 1 times the charge on 2 over the distance squared. Okay, so let's go ahead and write this out. So force equals, and I always put scientific notation numbers in parentheses. I think it's a good practice. Otherwise, it can be a little confusing. They can look a little hard to read. So it's 10 to the 9th Now, its force, it's going to end up in newtons, so you can be sometimes a little lazy when you know what the unit of measure is going to be at the end and not put them down, but I want to go ahead and be proper. So it's newtons, meters squared, over Coulomb squared. Close the parenthesis, and now charge 1, and it doesn't matter what order you put these in because it's a multiplication, you can multiply in either order, is 5 microcoulombs. So that's 5 times 10 to the minus 6, that we just said that's what a micro is, coulombs. And the other one is 7, but it's a negative charge, and it's going to be attracted, so we're going to say negative 7 times 10 to the negative 6th. Again, it's a micro, and that's also coulombs. And now we put all of that over the distance squared. And distance squared is 0.8 meters squared. Now I realized in doing this that some of you may not know how to cancel fraction over fraction. That can be tricky for some of you, so I'll put together a video on that. But for right now, you have coulombs, 2 coulombs in the denominator. That's coulombs times coulombs right there. That's in the denominator, that's in the bottom of the numerator fraction. This is a numerator fraction because it's up on top. So in the bottom of the numerator fraction, you have 2 C's, and you have a C here and a C here on the top. So these cancel. And then in the top of the numerator fraction, you have meters squared. And here in the bottom of the numerator fraction, you have meters squared. So so that's going to cancel those two with this. I don't want to cancel this because I want to square that number at the end. All right, what I would recommend you do is take this one step at a time. Multiply 8.9 times 5 times negative 7 and divide by 0.8. Go ahead and do that first. Take care of the coefficients. Remember, in scientific notation, we multiply and divide coefficients, okay? So it's a multiplication of these 3 coefficients, division by this. It's not in scientific notation, but you just divide by that. So what I'm going to do is this. It's 8. Okay, it's 8.8. It's actually, it should be 99. 8.99. I'm trying to get it so there's no glare on the screen, times 5 times, and now it's a negative sign for negative 7 is this minus sign. Not this is the minus sign, this is the negative sign. Don't get them confused. It's times negative 7, and it's divided by 0.8. And that gives you negative 393.3 times 10. And now what you have to do is take care of the exponents. So it's this exponent, 9 minus 6 minus 6. So that's 9 minus 6 is 3. And you minus another 6, and that gets you to negative 3. So it's 10 to the negative third. And the units of measure, the only one left standing, I should have pointed out after you did all these cancellations here, is newtons. And that's what you want your final answer to be in. Now, scientific notation says this should be a number between 1 and 10, or in this case, let's clarify that, between negative 1 and negative 10. In other words, the decimal should be right here. So we're going to move this number over to here. Okay. For right now, ignore the negative sign. Just 393.3. You made this number smaller, so it's 3.933 times 10. And therefore, you have to make this number bigger. So that's times 10 to the negative 1. Okay, and you can simply express that as negative, I'm going to move the decimal over here and just turn it into a decimal number. You don't have to do that, but they tend to do that in these lessons. So that's going to be 0.393 newtons. and that's the final answer for that. So that's the amount of force between those two charges of that strength at that distance. All right, so here's another problem, very similar problem. They give you two charges. They give you a distance, and of course you know Coulomb's law. So I'm going to do this silently and speed up the video. You can watch me, and then we'll go over it when I finish. Okay, let's go over this. So the force, you always start with Coulomb's constant. And the first charge is 6 microcoulombs. Again, that symbol. And again, go over to this sheet right here to look up any symbols you see like that. There's micro, 10 to the minus 6th, times 2 times 10 to the minus 6th over 0.1 squared. So the first thing I do is multiply this times this times this, so 8.99 times 6 times 2 divided by 0.1, and that's 0.1 squared. And that gives me 10,788, and then I take care of the exponents. Negative 9 plus negative 6 get you to, I'm sorry, that should be positive 9. 9 plus negative 6 gets you to 3. Minus 6 again gets you to negative 3. Now, I did something a little different than I told you on the scientific notation video, and that's because they decide to express their answers without scientific notation. Generally, that's not done. If you start with scientific notation, end with scientific notation. But they wanted this to be just a regular decimal number. So what I had to do is, instead of moving the decimal to make this a number between 1 and 10, I just moved the decimal as many places as that told me to move it to get rid of the decimal, to make that 10 to the 0. So when I move it over 3 places in this direction, it gets me to 10.778, which they called 10.8. They rounded it. Times 10 to the 0. Now I would have times 10 to the 0, which is 1. So that's how you get it out of scientific notation. So that's the answer that they came up with. But I would, if that last part of the explanation sounded a little messy, I would recommend you just leave it in scientific notation. But you should know that that's what the number that would represent as a regular decimal number. Okay, now we're going to move on to their big problem in the lesson. And that's one where you're going to deal with 3 charges. Can I tell you, this is an AP advanced placement level problem. This is not California standards to deal with 3 charges, but they've done it, so let's do it. Okay, so the rules for 2-dimensional vector force problems. Once you're dealing with 3 different points, in other words, one here, one here, and one here, you're dealing with forces not just in the x direction like these last 2 problems had, but in the x and y direction. So that makes the problem considerably more complicated. So here are the rules. You don't memorize these. You just have this in front of you all the time. So first of all, define what the vectors are. Calculate the length of the vectors. Define the vectors means what direction they're going in. And they did that for you in the problem. Calculate x and y components, that is the parts. So you want to, in other words, take a vector like this, and go back to the vectors video if you haven't watched that. You want to take a vector like that and break it into its x component, that's horizontal, and its straight up and down or vertical y component. That way you can add 2 vectors. Sum the vector components a and b, so you would add the y component of one vector with the y of another, and the x of one vector with the x of the other. Then calculate the magnitude of r, the resultant vector, and you do that using the Pythagorean Theorem, and then calculate the direction of the angle of that vector, and that's called theta r, theta resultant. Okay, so again, don't memorize these rules. What I would do is just go down them as a checklist each time you do one of these problems. So let's go ahead and get started on that. Okay, so here we go. This problem has a lot to handle. It says a 3 microcoulomb charge Q1. So here that is right there. There's the first charge right there. That's Q1, 3 microcoulombs. And a 6 microcoulomb charge Q2. There it is right there. And it says they are 0.05 meters from the x-axis. So if this is the x-axis right here, each one is 0.05 and 0.05 right there. So that's laid out for you. They drew this picture for you for the most part, but they didn't fill in all the numbers that I have here. So let's read this. Okay, and then it says a 6 microcoulomb charge Q3 is 0.12 meters from the y-axis. So in other words, you go in between these two. They didn't really make that clear that it's exactly going to be halfway between these two, but it is. But I'll tell you how you know that in a second. So there's Q3, and it says that it is 6 microcoulombs also. All right, and it says that it's 0.12 meters, there it is, from the y-axis. So it's on the x-axis, but it's 0.12 meters from the y-axis. Then it says the distance 1,3. So sometimes you have to learn how to read this, symbolism that they're using here. D13 means the distance from charge 1 to charge 3. And D23, that's the distance from charge 2 to charge 3. And it says that both of those are 0.13 meters. So right along this dashed line there, you can put D3, that's distance from Q1 to Q3, is 0.13 meters. And this one, D23, the distance from Q2 to Q3, is also 0.1. So they're both equal distant from this charge right here. It says find the magnitude and direction of the resulting vector force. So these two are pushing on this one right here. So the first step is define the vectors. Well, if this is pushing on this charge, it's going to push it directly away in this direction right here. And if this is pushing the charge in this direction, it's going to push it in this direction here. So that's the direction of your arrows. But how long should those arrows be? Well, let me show you real quickly. Let's write a Coulomb's law, just a general Coulomb's law without all the numbers for, well, we can do it with the numbers. Let's do that. So force between 1 and 3, that's F13, equals K. And I'll just write it K for right now. The charge 1 is 3 microcoulombs. And charge Q3, that's the other charge, we're only interested in these two charges right now, is 6 microcoulombs. And the distance is between these two is 0.13 squared. Now let's write it for these two, the force between Q2 and Q3. So that's going to be F23 equals K. I'm not going to actually crunch the numbers right now. That's why I'm just writing it in shorthand here. And that's going to be 6 coulombs, microcoulombs. That's Q2. And then Q3 also, just like it was in this equation, is also 6 microcoulombs. So it's this 6 microcoulombs here and this 6 microcoulombs there. And again, the distance is the same. So it's 0.13 meters squared. So we're just kind of looking at this conceptually. And that should be meters squared. Okay, so the distances are the same. The Coulomb's constant is the same. Charge 3, Q3, is the same. That's this one right here. What you'll notice is different is that this charge, which is charge 2, Q2, is twice as strong as charge Q1. That means if this number is double this number, then the force here is going to be twice as much as the force here. We don't know what that number is yet, but we're just trying to understand the vector. So this one is going to have twice as long a vector as this one because it has twice as much force. So it doesn't matter exactly how long you draw these vectors. You're going to assign numbers to them later. What you should draw is this vector should be twice as long as this vector. Okay? So we've identified the vectors and the relative length. Relative means this one is twice as long as this one. We don't know what that number is yet. We just know it's twice as long. Again, let me say that again. Every number in the force equation between these two particles and these two particles is the same except the charge. 6 versus 3. So if we put a 6 there versus a 3 there, it means that this number is going to be twice as big as this force number. That means its vector, the vector from force 2 to 3, that's this one right here, is going to be twice as big as the vector force 1 to 3. So this line is twice as long as this line. All right, so that's, I'll just put C diagram, and that's where you'll get that explanation. Okay, so step 2 is calculate the magnitudes for A and B using Coulomb's law equation. So that's what I avoided doing in step 1, but let's go ahead and do it now. Sometimes it's a little challenge for me to keep everything on the screen that I want on the screen. I'll do the best I can. So the force between charge 1 and charge 3, again, this is 3 microcoulombs, this is 6 microcoulombs. So now we're going to actually write, so F13, the force between 1 and 3 equals, now we're going to actually write out the numbers. 8.99 Okay, I pointed to this one accidentally. We're only interested in this relationship right now. We're not paying any attention to this relationship. Okay, and that's over the distance, this distance right here squared, so that's 0.13 meters squared. Okay, and I'm going to go ahead and write this, the force equation before I even solve this. I'm going to go ahead and write the force equation between these two. So that's going to be force 2-3. Try to keep it on the screen as much as possible. Okay, now we're dealing with this charge right here. That's 6 times 10 to the negative 6th. Again, micro is 10 to the minus 6 coulombs. And now we're dealing with this charge. It wouldn't have been nice if they made them different numbers so you didn't get them confused. But this is also 6 microcoulombs. And that entire numerator of that fraction, numerator is the top of a fraction, is also going to be on over 0.13. That's this distance. They both have the same distance, 0.13 meters squared. Okay, and now I'm going to punch those in the calculator. Again, this part might be confusing to you, so kind of watch. I'm going to take anything that's not a 10 to the power or something and multiply it on the top. This times this times this. And then I'm going to divide it by 0.13, but don't forget to square it on the bottom. So here we go. Try to show it without it glaring too much. 8.99. Here. 8.99 times, I'm doing the top equation here, 3 times 6 times 3 times 3 times 6. And now I'm going to divide it by 0.13 squared. 0.13 x squared. There it is right there, x squared. So that's 0.13 x squared. I divided by, and I hit equal. And I get 9,575. Again, we don't want to go out this many decimals or even close. So I'm going to call it 9,575 times 10. Okay, and it's 9 minus 6 is 3 minus 6 again. We keep coming up with those numbers, is negative 3 to the negative third. So the decimal is right here. If I want to convert that into just a regular number, regular decimal number, that means I've got to go in the direction that makes this number smaller because it's a negative 3, 3 places. So 1, 2, 3. It goes between the 9 and the 5. And they rounded that to be 9.6, and that's all the decimal places we need. So it's 9.6 newtons of force on this one. Okay, now you can do the same thing for this problem, or you can be a little bit clever. These two numbers are the same. These two numbers are the same. These numbers down here are the same. The only numbers that are different is this 6 is twice this 3. And I talked about that up at the top. Since this number is twice this number, that's the only difference between these two equations, then this force is going to be twice that force. So if you want to practice, you can go ahead and run that there, or I could simply take this force, 9.6, and double it, and that's going to give me 19.2 newtons. Okay. Now if you want to draw that on your diagram here, what you're going to say is B, the force on B, is going to equal, now this is the one between 1 and 3, get back on screen a little bit, between these two that's creating this vector, that's 9.6. So that's going to be 9.6. So that's going to be the length of that vector. We were saying, well, we don't know what the length is. We just know it's going to be only half as long as this vector. This one's twice as long as this one. So this one's 9.6, and A up here is 19.2 newtons. Okay? So this number is twice that number simply because the only difference between these two equations that you wrote for the force on the two charges is that this one is twice as great as that. That makes the force twice as great as that, 19.2 versus 9.6. Okay, so that takes care of step 2. Okay, the next step, it says, is to calculate the x and y components, including angles for each vector. This is a part that gets us a little bit deep into some geometry here, okay? So if you didn't watch the videos on vectors and on scientific notation, and what I'm about to say is on the video, is in the video on, not scientific notation, on trigonometry. Actually, all three of them, scientific notation, vectors, and trig. But really, this one is in the video about trig. I gave a couple of geometry principles, and here's one of them. Here's the first one. These two angles, this angle right here, we don't know what theta b is. There's no way we can know that directly. But we know that this angle is equal to this angle. Those are called vertical angles. So this is theta b, this angle right here. So if we can figure out what theta b is here, we'll know what theta b is here. They're the same angles because they're called vertical angles. Again, if I draw a line, forget about this charge and this line for right now. Forget about it. Between this line and the x-axis, like that, then these two create vertical angles. Theta b, theta b. Okay, so how do we figure out what theta b is? Well, we can do it over on this side. And if you remember that this is theta, then this is going to be your adjacent side. This triangle is backwards from the ones that we did in the trigonometry video, but it doesn't matter. This is the adjacent side because it's right next to the angle. This is the opposite side because it's on the opposite side of this triangle. I'm talking about this triangle right here, by the way. This triangle right here. So I'm tracing it out, so just kind of lightly trace that out with your pencil. This is on the opposite side. And this is the hypotenuse over here, but we won't really need that right now. We could use it if we wanted. Okay, so to figure out theta b, how do we do that? We use an inverse function. Okay, remember, if you're given sides, and we know all three sides of this triangle that I'm tracing out right now, this side is 0.12, this side is 0.05, and this side is 0.13. So we know all three sides. We can use whichever one we want. So what I'm going to do is I'm going to go ahead and use, it doesn't matter, I am going to use opposite over adjacent. Now go back to your trigonometric functions that are in the trigonometry video, and I realize it's a 40-minute video, but if you're not really strong in trigonometry, you need to watch that. So we're going to do opposite over adjacent. What function is that? Or what trigonometric function? That is a tangent. It's the opposite of the triangle over the adjacent. So that means if I do the inverse tangent of 0.05 over 0.12, that will give me theta b. That will give me this angle. Okay, so I'm going to come back here and I'm going to write that out. Okay, so what I've done is I've taken this triangle with this side of 0.12, this side, the opposite side, that was the adjacent, the opposite side of 0.05, and the hypotenuse of 0.13, and I've recreated them right here. So just that triangle with nothing else. So how do we find theta? Again, you could use the sine, cosine, or tangent functions. I'm going to use tangent. I'm going to use this over this. So remember what we did. We said that the tangent of theta is equal to the opposite over the adjacent. And that's this over this. So that equals 0.05 over 0.12. Okay? So tangent equals this. But I want to unwrap this. I want to get this out. So I use the inverse tangent function. Remember, an inverse just undoes this. So if I take the tangent of theta and then I take the inverse tangent of theta, that just gives me theta. And that's going to equal the inverse tangent. Anything you do to one side in a math equation, I added an inverse tangent to this side. So now I have to add an inverse tangent to the other side. Okay, so what I'll end up with down here is theta equals inverse tangent of these two numbers, opposite over adjacent. And when we do that on the calculator, how do you do that? You come up here and you go to second tangent. So now you see I have inverse tangent, tangent to the -1. I'm trying to avoid the glare here. Tangent to the -1 of 0.05 divided by 0.12. I close the parenthesis, and that gives me an angle of 22.6 degrees. So that means this angle is 22.6 degrees. That's theta B. But going back to our original sheet, this angle is 22.6 degrees. That means this angle is 22.6. I'm going to draw it down here. I don't want this to get too crowded up here. It was already too crowded on the video, and that was my problem with their video. So that's 22.6 degrees. Again, go back and review the trigonometry video if that was faked out, okay? If you didn't get that, you got to watch the trigonometry video. Now, what about this one down here? What's this angle here? Well, it's the same as this angle, which is theta A. Now, it's an upside down and backwards triangle from the ones we did on the trigonometry video, but just to understand which side is which. This is still the adjacent, so I wrote adjacent there for this one. It's also the adjacent for this one. There's your angle, there's your adjacent side. Here's your hypotenuse, here, and here's your opposite. So we have exactly the same opposite and adjacent as we had for this triangle we have for this one. Again, the triangle's upside down from what we saw in the videos, but it's the same thing. This is the adjacent, is 0.12. This is the opposite, 0.015. So it's exactly the same equation. That means you're going to end up with exactly the same angle up here, and I'm going to write it up here, is 22.6 degrees. And I believe they rounded that to 23 in the video. So I'm going to go ahead and do that. I'm going to round that off to 23. So both of these angles are 23 degrees. Okay? So I'm going to go ahead and just write that down. This is theta of B. And theta of A, I'm just going to go ahead and assert it because we just saw how it works the same, is also 22.6, and I'll change that to 23 here in just a minute. So let's just write it, 23 degrees. That's what we're going to use. Okay? All right, now we have to calculate the components, and then we have to sum them. So it says calculate the components up here. I don't have enough space to do that. I just did the angles. So let me go ahead and calculate them down here, and I'll sum them down here. So let's go ahead and do that. Okay, so here it is right here. And I'll move the camera in a little tighter now. I know that this hypotenuse of this right triangle is 19.6. That's this right here. And I need to figure out this AX component going horizontally and the AY going up and down vertically. So how do we do this? Well, we know that this is the opposite over here. I'll just write that real lightly. And this is the adjacent down here. And this is the hypotenuse. So for AY, we know that opposite over hypotenuse equals the sine. That's the definition of sine. It's opposite over hypotenuse. So the sine of 23 equals opposite, that's what we're trying to find, over 19.6. Okay? That'll give you the opposite side. And what do? We did this several times in the trigonometry video. We multiply both sides by 19.6. These cancel, and now you have opposite all by itself equals 19.6 newtons times the sine of 23 degrees. Okay? So let's go ahead and punch that in on the calculator. 19.6 times sine of 23. It's a little blurry because I'm holding it up too close to the camera. Close the parenthesis, and that gives us 7.7. Let's round that to 7.7. So this side right here is 7.7 newtons. Now let's do the AX. So this was the Y component, AY. Now let's do AX. It doesn't matter which order you do them in. So now we're going to do AX over here. Don't want it to become too crowded here. AX. So AX, this is the adjacent side to the angle. Adjacent over hypotenuse is going to be the cosine. So the cosine of 23 equals our adjacent, that's the unknown we're trying to find, over the hypotenuse, which is also 19.6 again. Okay? Multiply both sides by 19.6. That should be the decimal, should be there. That cancels. And over here, I didn't leave myself any space, so let me get rid of that AX right there. Need that space right there. And this is 19.6 also. This is AX. Okay, cancel, cancel. So you end up with the adjacent. That's this side right here. Equals 19.6. I keep putting the decimal there. 19.6 times cosine of 23. Okay, so I have 19.6 times cosine of 23 degrees. Close the parentheses, so that's what it looks like. The 9 went off the screen, but it's there. Okay, and that equals 18. We're just going to call that 18. So this equals 18. All right, if I go back to my original drawing, again, it gets a little crowded. It really did on theirs. So that means this value right here is 18. I'll write it really small. And this value right here is 7.7. Okay? There you go. Let me get this thing straight out. Okay. So this is 18. This is 7.7. With a small, relatively small angle of 22 degrees, this side's going to be pretty close in length to this side. Okay, it's actually a little bit tighter angle, but I drew it bigger so I could fit all these numbers in here. But if I had drawn it, the angle would have been more like this. It would have been a lot lower down. And they drew it on the screen like that, and it was hard to read. Okay, so let's go ahead and okay that. Now we're going to do it for the other one. You got to do it again. All right? So you have the same angle here of 23 degrees. Change that to 23. So let's do the same thing over there. Okay, so I'm going to kind of segment this off like this. And now we're going to do for B. And I'll draw the triangle the way that it's drawn there. Okay, so there it is. So what I've drawn here is, whoops, I didn't draw that right. Sorry, it's on the top. I want it to look exactly like the diagram, and I didn't. Let's do this. Okay, so I've drawn that to make it look exactly like this. Here's bx, here's by. It's going in the negative direction because it's going down from the x-axis. And then here's the hypotenuse, that's the vector itself, and that's 9.6. We determined that earlier. So that's what it looks like right there. So here's your angle theta, is 23 degrees. All right, so what is bx? Bx is, so this is the adjacent. Identify your sides. ADJ, again, adjacent is next to the angle, but it's not the hypotenuse. That's the hypotenuse. The one next to the angle that's the longest is the hypotenuse. The other one that's next to the angle is called the adjacent, and this one is called the opposite. So for me to get bx, okay, what I need to do is I need to say bx, that's the adjacent, over the hypotenuse. What function is that? Adjacent over hypotenuse is cosine. So the cosine, and technically, because this is going down like this, it's negative 23 degrees. That makes it a little trickier. They didn't show you that in the video. They just kind of put on a negative sign out of nowhere. But whenever you go backwards like this, you go in this direction, it's negative. You're going in the negative direction for your angle. Okay, so we're going to call that negative 23 degrees, and that was a flaw in the video. Okay, so cosine of 23 times cosine of 23, excuse me, equals adjacent over 9.6. That's the hypotenuse. Adjacent over hypotenuse. Okay. I'm going to skip the algebra step. You know that you're supposed to multiply. I won't. I don't want to skip any steps. 9.6 on this side. And again, I need that space there. And 9.6 on this side. Cancel, cancel. And you get 9.6 times cosine. I'm going to put a negative 23. Again, it's this button, not this button. This is a subtraction button. This is a negative sign button. Negative 23 degrees. I'm going to close the parenthesis, and I get 8.8. Okay, so this is 8.8 newtons. All right, that's for the x component. So this is 8.8 up here. This part right here. Now we're going to do this part. So that is, what is that? Opposite over hypotenuse is the sine. Opposite over hypotenuse is the sine. So we're going to say sine of negative 23 degrees. Because again, we're not going up this way, that's positive. We're going down this way, that's negative. Sine of negative 23 degrees equals the opposite over 9.6, the hypotenuse. Okay, multiply both sides by 9.6. 9.6. Cancel, cancel. And your opposite equals 9.6 times sine of negative 23. So that's going to give us this. 9.6 times sine, negative sign down here, 23 degrees, close the parentheses, and equal, and it gives you negative 3.75, we'll call it 3.8, negative 3.8. Okay, now we're ready to add. So the x components, I'll just abbreviate that comp, x components are going to be 8.8 here, and if we come over here, it's going to be, where did I write it? Well, I write it right here. It's 18. So it's 18 there. Let me go ahead and write this here, by the way. So this is negative 3.8 newtons, and this one was 8.8. So the x components are going to be 8.8 here and 18 here, and they're both going in the positive direction. Remember, you start at the tail, the end of the vector that has of the resultant vector that has no arrow, and you go over to the right, that's positive, and down, that's negative for y. For this one over here, you start at the tail, you go over to the right, that's positive, so both of the x components are positive, and then this y component is positive, is positive as well, so both of these are positive. So we're first going to do the x components. That's 18, and that's 8.8. So this right here, and this, sorry, off screen, this right here. All right, what I need to do, I'm sorry, I needed to bring that back up. That's why I'm so tight in there. Okay, so let me do that again. This is the x component for this one, and this is the x component for this one. So it's 18.0, we'll just call it, and 8.8. You add those together and you get 26.8 newtons for the x components. For the y component, what are they? This is the y component here, that's 7.7, and that's positive. And then this one here, it's going down, and that was our negative 3.8 that we got. So it's negative 3.8 newtons. Okay, and you subtract those. And you get 3.9. A positive 3.9. Okay, so now we have to calculate the resultant vector. So let me go ahead and write all of this over here. For bx right here, I got an 8.8. I know it's really small, that's why I'm drawing it separately. That was bx, and for by, on this one we got negative 3.8. So that's this one right here, negative 3.8. Okay, so I added 7.7 minus 3.8 for the y components, and for the x components it was 8.8 and 18, written really small right there, 18 plus 8.8. Alright, so now I have my x and y components of my resultant. So now let's go ahead and draw that resultant here. That's going to be a longer vector. And this is called the resultant, and the x coordinate of that resultant is going to be adding those two x coordinates we just did and the y coordinates. So this is resultant y coordinate. I am off screen, I'm sorry. This is resultant y coordinate, and this is resultant x coordinate. Okay, and we just calculated what those were. For the y, it's 3.9 newtons. And for the x, it equals 26.8. Okay, now we use the Pythagorean theorem. No more trigonometry. Good old Pythagorean theorem. A squared plus b squared equals c squared. Okay, it doesn't matter which one you call a, but this one's always c. The hypotenuse is always c. So let's call this one a and this one b. So 26.8 squared plus 3.9 squared equals c squared. When I add those two, I'll come over here. 28 squared. So I do 2/8, and then I hit the x squared button here. Now PEMDAS is going to know that a square comes before an addition, so I can just go ahead and pop in a plus sign there. It will do the square before it adds, and it will do the other square, which is 3.9 x squared. So there you go. You have 28 squared plus 3.9 squared. It will do the exponents first, and then it will add the two numbers together. And that equals this. 799, let's just call it 800. So c squared equals 800. Now what I'm going to do is I'll show you how to use a calculator here a little bit. Let me get down lower so you can see the whole thing. I have a store down here. When I hit store, now there's something in memory cell A already, but that's something old. I don't need it anymore. So I don't care if I erase over it. So I hit store and I'm going to hit equal. And what it did is it took what I had in the screen and it put into memory cell A. All right, and I'll show you why I'm doing that in a second, because I need to take a square root. And on this type of calculator, you have to put the square root sign in first and then the number. Not all calculators do that. You might have one where you can just put the number, hit square root, and bam, you got your square root, but not on this one. So now that I've done that, it's in A, I'm going to clear it. Now, square root is the second function of x squared. I know this is a lot to absorb today, guys, but it just, it'll pay off down the road. So there's the square root sign. So I hit second, x squared, which will bring up the square root because I hit the second button. It gives me an opening parenthesis. Now watch what I do. I hit, above the store is a recall. So I hit second and then store, but what that's going to do is recall memory cell A. That. And I hit equal. And now I want to close the parenthesis. So that's how you take the square root of a number. You have to put the square root sign up first on a TI-30 and then put the number in, close the parenthesis, and that gives you 28.27. We're going to call it 28.3. So that means that C equals the square root of this. If you take the square root of, let me get my calculator out of the way, get the square root of both sides here, and then C will give you 28.3 newtons. That's the hypotenuse. That means 28.3 newtons is the magnitude of the resultant vector. Okay? There you go. So now you have three sides of this resultant vector's triangle, and the last thing it's asking you to do is calculate the direction. So you can use whatever you want. Again, here's 23 degrees. Oh no, I'm sorry, it's not 23. That's the theta we're trying to find. I apologize. This is some theta. This is the resultant theta. It's not the 23 degrees we were using before. It's a new vector. So we can do it either this way. We can do the sine, 3.9 over 28.3. We can do the cosine, 26.8 over 28.3. Or we can do the tangent, 3.9 over 26. Let's go ahead and just use the sine here. Okay? So sine of theta, this is an inverse operation, equals opposite. Let's just write it out. Every time I do a problem, I always write out the formula, and that way you end up memorizing them without trying to memorize them. Opposite over hypotenuse, which in this case is 3.9 newtons over 28.3 newtons. Okay, so sine of that. So let me just write it cleanly. Sine of theta equals So now what I want to do is I want to take the inverse of this because I want to unwrap theta and get it out of there. So I take the inverse sine. Okay, that means I need to, let me do that down below. I didn't give myself enough room. Sine -1 sine of theta. And I'm off screen, I'm sorry. Sine of theta equals inverse sine. Anything you do to one side, you have to do to the other, of 3.9 over 28.3. Okay, and this will give me theta. This whole thing just, it unwraps the theta from the sine because you reverse it, sine of theta, and then you reverse that to just get theta, equals this. Okay, so let's do that. So it's second sine, that gives me the inverse sine of 3.9 over 28.3. 3.9 divided by 28.3, close the parenthesis, and you get an angle of 7.92, call it 7.9. Okay, so this angle equals 7.9 degrees. Okay, and that is the resultant. So let's go back to our original. What we ended up with here is a resultant. Okay, I'm going to back up. I made a slight error here. When I squared those, I punched in the wrong number. This should have been, it doesn't change everything. It just changes this to 733. And when I take the square root of that, I get 27. I think on the video they get 26.9. That's close enough, okay? So that's the magnitude of your resultant vector, and this is the angle of your resultant vector. So that's the correct answer, and that should be Newton's unit of measure. Okay, that was a lot to bite off. So what I am going to do is I'm going to end this video, and I'm going to do the other problems on another video. And this will be instruction problems part 1. And you'll see that in the Google Classroom under Coulomb's law. Okay, I'll see you on the next video. Again, go back and watch trigonometry, scientific notation, and vectors if you still need help in those areas. Okay, see you next time.